Okay, so this video we're talking about quadratic linear systems, right? And that's just a fancy way of saying that we're graphing a line and a parabola on the same set of axes. There's a couple of ways to do it. One way is to do it graphically, and the other way is to do it algebraically. You should try the do now problems, but I'm not going to go over that in this video. If you have any questions, send me a message, but the answer key is online. All right, so in order to graph a quadratic linear system, solve it graphically, we're going to need to have a nice consistent way to graph both the parabola and also the lines. All right, so now as far as the line goes, that should be the easy part, but sometimes they write it in a form that's not user friendly. So I'm going to start with that and graph this once I convert it into y equals mx plus b form. So I'm going to subtract the 2x from both sides. There's a bunch of ways you can do it, but this is the way I choose to do it. So I'll have negative y is equal to negative 2x plus 3. Then I'm going to negate both sides and get y equals 2x minus 3. So I'm multiplying both sides by negative 1. That should be easy enough to graph, but I don't want to graph anything until I've gotten the particulars for each function. Right? The reason why that's of great importance is because you don't know necessarily that the parabola is going to be of the same scale as the line. So you might have to scale your graph. If you start graphing your line and then later on find out that you needed to change the scale, that could be a problem. All right. What I'm going to do is I'm going to get my parabola in standard form. In this case, this is a perfect square trinomial. All right, both the first and last term are perfect. So if I write this as x minus 1 squared, I'd have an equivalent relationship. All right, so then I would have my vertex at negative 1, 0, positive 1, 0, sorry. And I could create a table of values. I could put it in my calculator, or I could use the 149 relationship. Right? So the 149 relationship is just telling me that for every unit that I go out in terms of x, I'm going to increase by 1 times the a value, 4 times the a value, and 9 times the a value. All right, so I'll make a little note of that if you're interested. Otherwise, use the calculator. So the 149 method for each 1 unit in x, increase or decrease y by 1 times a, 4 times a, and that's poor quality a, it looks more like a 9, and 9 times a. All right. An alarm went off. All right, so I'm going to plot 1, 0. The a value for this function was a 1. So for my first step out in a horizontal direction, I'm only going to go up 1 unit. For my second step out, I'm going to go up 1, 2, 3, 4 units. And for my third step out, I'm going to go up 9. And I'm going to do the same, because it's symmetrical, I'll do the same in the opposite direction. If I wanted to, I could have gone again with the table of values, but this is easy enough. Because the a value is equal to 1, it's really just that relationship. If the a value were equal to, let's say, 3, then instead of going 1, 4, 9, I would go 3, 12, 27. Obviously, I wouldn't plot the 27. All right, so this is my, I already forgot what it was, y equals x plus 1, minus 1. All right, the other equation was 2x minus 3. So I'll go down 3. And a slope of up to over 1. Up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and so on. All right, so it looks like it's just barely going to touch this parabola in the one location. And I'm just going to label this because it's two equations on the same set of axes, so you want to make sure you label each of the graphs to distinguish them from one another. Most directions will suggest that you need to do that. All right, what we're looking for is the intersection. Here it's 2, 1. So that is the solution to the quadratic linear system. All right. And all your work should just be right on the graph. Now it says, verify your solutions by solving the system algebraically. Now, an algebraic solution does not involve you just taking your answer to the graphical one and plugging it into the algebraic one. It involves you using a substitution method, or at least for quadratic linear systems. So I have y equals x squared minus 2x plus 1. And then we have 2x minus y equals 3. So the algebraic solution would be, since I know that y is equal to this whole expression, I can replace the y in my second equation with that expression. All right? There's other ways to do it, but this is the way I'm choosing to do it. So we're looking at 2x minus the entire expression x squared minus 2x plus 1. At which point we can distribute. I have a -1, understood -1 here. Gets distributed to each term. Combine our like terms. I have a 2x and a 2x, so I'm going to be looking at, in its current form, negative x squared plus 2x plus 4x. I could also subtract off the 3 minus 4. Whole things equal to 0. Now it's a matter of deciding which technique you want to use to solve. Right? Factoring is always the preferred choice because it's usually the easiest one to do. All right. So here I notice I have a leading coefficient of -1, so I'm going to pull that out. X squared minus 4x plus 4. So that happens to be another one of those beautiful perfect square trinomials. So I'm looking at -1 times x minus 2 squared is equal to 0. Now if I want to solve this, I can divide both sides by -1, which gives me x minus 2 squared equals 0. I want to get rid of a power of 2. I can take the square root of both sides, which gives me x minus 2 is equal to 0. I don't have to worry about a plus or minus because plus or minus 0 is still 0. And then if I add 2 to both sides, I get x equals 2. All right, now that's not my final answer because I need the y value that corresponds with that x value, but it's a good step because what I can do is I can kind of be a little sneaky about this. I can go back to some of the work that I did in part A, or yeah, I guess I'd call it part A. This part of the problem, we had discovered that y was equal to 2x minus 3. And so now I know that x is equal to 2, so y is equal to 2 times that 2 minus 3, in which case I get y equals 1, and so therefore my solution to the quadratic linear system would be the coordinates 2, 1, which is what we came up with graphically. Now, you'd be right in saying that the graphical solution seems to be a lot simpler than the algebraic solution. There's a time and place for everything, but this is one of those situations where you might look at it and say, well, why do I have to do it this way? For that, the only thing I can tell you is down the line, you're going to have strong algebra skills, and so this is an attempt to kind of help you to refine your abilities in that area. And there it is. So just continuing the lesson on quadratic linear systems. Number 2, solve the following quadratic linear system graphically. In an ideal world, we'd have quadratics that are written in a form quite like this, because this could be thought of as x minus 0 squared minus 9. So I got my vertex, just jot it right here, 0, negative 9. My linear equation, all I have to do is move that 9 over. And now, using whatever technique I want, I can graph my parabola, and I could also graph my line. I still got to get it on paper, but it's not going to be too difficult. So there's my line, or at least it will be in a second. Slope of 3. Use my line draw tool. Shaky line, not so shaky anymore. See if I can straighten that out a little bit. Y equals 3x minus 9. For the parabola, a slope, or I'm sorry, a 1 unit slope of 1, so it's still the straight 1, 4, 9 relationship. So up 1, 2, 3, 4, 5, 6, 7, 8, 9, and then use my symmetry. And again, if you want, go right to the calculator. There's no reason why you have to use fancy shortcuts, although it's a cool fancy shortcut if I do say so myself. All right, so it looks like I have my 2 solutions here. Three, 0, and 0, negative 9. All right, again, all the work right on the graph, that's all you need. Algebraically, it's the same idea as before. We know that y is equivalent to x squared minus 9. I'm going to replace the y in my second equation with x squared minus 9. So, I hate when I do that. X squared minus 9 plus 9 equals 3x. The negative 9 and the positive 9 go to 0, so I have x squared equals 3x. It's quadratic, so let me get everything over to the same side. I have a GCF of x that I can pull out. And then I could set each factor equal to 0 and solve, and I get x equals 0, and I get x equals 3. Right, so then it's just a matter of figuring out what the y value is that corresponds with each one of these x values. So that makes it a little trickier. But again, can be a little sneaky and use some information that we figured out in the first part of the problem. 3x minus 9 is what y is equivalent to. So I'm going to figure out y of 0, replacing each of the x values, or in this case only one x value, with a 0, and I get a negative 9. And then figure out y of 3, same deal, in either case, I get my solution, right? So, or I get solutions. So the 0 corresponds with a -9. The 3 corresponds with a 0. So those would be my solutions. All right. Some are easier than others. The last one, number 1 on the previous page, was definitely easier because there was only one solution. But you'll see as you move forward that some of them are not difficult at all, and some of them take a little doing. All right. Number 3, we have a little bit of background work to do first, but nothing too crazy. I want to move this over. So I'm looking at y equals x squared minus 1. So I have a vertex at 0, -1. Here I have y equals -x plus 1. All right, so going right into my graph, vertex at 0, -1, the 1, 4, 9 relationship. The other one was -x plus 1. So y-intercept of 1 and the slope of -1. You don't have to go too far before you see what the solutions are here. Alright, so we're looking at this guy right here and this guy right here. Our solutions would be 1, 0, and it looks like -2, 3. I don't need to check it because I'm about to do that algebraically. So if I get something other than 1, 0 and -2, 3, I'll know to go back and look at my work again. Alright, so here I'm going to work with the modified version of my linear function because I know that, ooh, that did not look good. I know that y is equivalent to -x plus 1. And I also know that y minus x squared is equal to, minus x squared is equal to -1. So I'm going to replace that y with a -x plus 1. Then I'm going to combine my like terms if there are any. It doesn't look like it, at least not yet. So I'm going to reorganize into the first galactic empire. Movie reference. That's the Easter egg for this episode. If you message me with that Easter egg, you will receive 1 bonus point. First come, first serve. So I have -x squared minus x plus 1. It's quadratic, so if I'm going to solve, I need to get that 1 over to the other side. We're always going to try to do it using a factoring technique first and settle for things like quadratic formula and completing the square. All right, although it said algebraically, so we want to stay away from quadratic formula. X squared plus x minus 2. Now, if you want to use an X chart, or if you want to kind of, I'll call it legally cheat. It's not really cheating, it's just kind of using your resources to its fullest potential. We already know what the answers are. We know that the x values are supposed to be 1 and -2. So we can kind of use that information to build our factors without having to go too crazy in terms of doing the work. So if we know that it's going to be 2 and 1 in some capacity, you could start playing around with the signage. It wouldn't take too long before you realize that one of them has to be positive and the other has to be negative. That's because the product is negative, and this would be the only arrangement that would give you a positive sum in the middle. All right, so Now I could take my two factors and set them equal to 0 and solve. In which case, then I'm just going to kind of cut to the chase here. I get x equals -2 and +1. Poor quality and symbol. Which coincides with what we have there. We also know that y is equal to x, or -x plus 1. So I'm going to compute y of -2 and y of 1. So -2 plus 1, -1 plus 1. So in the first case, I'm going to get 2 plus 1 is 3. And in the second case, -1 plus 1 is 0. So my solutions, -2, 3, and 1, 0. The x with its corresponding value of y. The last one's the nicest one. Not because it's the last one, but because it's great. It's a great problem. Very easy to graph. Y equals x plus 2. 2 units up. We could use the 1, 4, 9 relationship if that one's growing on you. 1, 4. Well, I run out of room there, so I'm not going to bother with the 9. And my graph's looking a little dicey here, so I'm going to undo a couple things. Looks like it was getting out of control here. It's really, as long as you're aiming for the right location, you don't actually have to have the point on the graph. Now, mine is starting to look a little too pointy at the bottom. And we generally want to stay away from that. It should be a nice U-shaped curve, not V-shaped. So I'm going to do my best to correct for that, but, you know, obviously there's a lot of wiggle room here. It's the points that are the most important piece. So that's y equals x squared plus 2. That's not the reason why this is such a nice problem. This is a nice problem because of the second equation, which is y equals 3. Horizontal line, 3 units above the x-axis. So we have our solutions without really doing much. Our solutions are going to be 1, 3 and -1, 3. All right, if I'm doing it by hand, it's not even that difficult because we already know what the y value is supposed to be. So half of the work is already done for us. I hate when I do that. Come on, get out of there. So I know that y is equal to 3. So I'm going to replace the y in one of the equations with a 3. So 3 is going to be equal to x squared plus 2. I'm going to subtract the 2 from both sides and get 1 equals x squared. I want to get rid of a power of 2, so I'm going to take the square root of both sides. In which case I'm going to get x equals plus or minus 1. All right, so that's two possibilities. X is equal to 1. X is equal to -1. All right, both of which correspond to a y value of 3. So my solution is very easy. -1, 3, and +1, 3. And there it is.